Thank you very much. Okay, so I will talk about one variation on the theme of ambient construction as emphasized in the title. So in particular, in one particular case, or one particular geometry, in fact, conformal geometry, I will try to add to these basic data, so the conformal structure, another data. Excuse me?
Turn the mic or turn the mic on.
It should be turned on. Does it work or? Okay, so I will try to speak a little bit loud. Is it okay? Fine. Okay, so once again, so the theme of my lecture should be to try to extend a little bit the basic data of conformal geometry to add to it certain additional data which consist of so-called finite reflection group as a subgroup of conformal group, and to undergo ambient construction with this new data, and the result should be construction of certain differential difference operators, which could be thought of as analogs of GJMS operators in ordinary conformal geometry. Okay, so I will try to explain what I mean by this. So usually in many cases, when talking about invariant theory for finite reflection group G, one usually considers this group as a subgroup of orthogonal group of say n-dimensional Euclidean space with quadratic form. The aim of this talk is to try to look at another problem. The aim is to consider finite reflection group G as a subgroup of conformal group, say of signature n+1,1, and to study so-called differential difference operators or G-invariant intertwining operators acting between induced representations, say in the flat case on the sphere as a flat model of conformal geometry, where this finite group once again is realized through its embedding in the conformal group. So, okay, so there are many questions one can pose. One of them are, of course, for example, what is the classification of such G-invariant differential difference operators on the sphere with the standard round matrix? In particular, what are G-invariant differential difference operators whose symbols are powers of the Laplace operator? So I will explain what symbols for such kind of operators mean, and for example, what happens on general conformal manifold when G is a finite subgroup of the group of automorphisms of conformal structure, and what are G-invariant homomorphisms of associated vector bundles. Okay, so in a couple of previous lectures, for example, Mike Eastwood, Robin Graham already explained what the ambient construction is. So the remaining data I will need is the notion of, it's necessary to explain the notion of reflection group. Okay, so starting with the vector space of signature PQ with corresponding quadratic form, so C will denote the cone of null vectors. So for any vector alpha which doesn't belong to this cone, we denote R alpha, the reflection along the hyperplane, which is orthogonal to this vector alpha, and the formula for how this reflection works is standard, so and is well known. So I will not repeat it. And so collection of vectors. So we say that a finite subset of such vectors is root system, provided these two technical conditions hold. So I don't know. The second is saying that the reflection along any element from this set is surjective when acting on the set of roots in the root system. Okay. So a subgroup of orthogonal group of of a quadratic form on vector space of signature PQ, which is generated by reflections, is called reflection group associated to the root system. And one more definition is needed, and this is the definition of so-called multiplicity function. So the reflection group is acting on roots in the root system, and this action generates certain equivalence relation. And then a function on the set of roots quotients through this equivalence relation, then this is a class function with respect to this equivalence relation. And this is by definition a function which is a class function is called multiplicity function. Okay, multiplicity function on the root system or associated to the root system. And the last device I have to recall is called so-called Danko differential difference operators. So this is certain modification of ordinary, say, on the Euclidean space R, on the space RPQ. So it's certain modification of ordinary coordinate derivatives, in a sense that this modification consists of, or is valued in the group ring of this reflection group, and it's proportional to the value of multiplicity function. So the multiplicity function is denoted by k. So while the first part of this operator is differential or differentiation in the direction of psi, the second part is non-local, obviously. So
What happens if you
what?
are something orthogonal to alpha? What does that dash mean?
Okay, so this operator should be evaluated on a function which is function of the variable x, where x is the vector in RPQ. So here, so then x should be here.
Right, and what if alpha is orthogonal to x?
No. The point is that when f or this element from the group ring is applied on f, so this cancel out. I mean, potentially this cancel out the singularity which could appear here. So, okay, yeah. So there is no singular behavior at all. Okay, so these operators, for example, when psi will run over coordinate directions, so this family of operators, depending on the multiplicity function k, is commutative but not G invariant. On the other hand, forming Laplace operator from these so-called Danko differential operators. So the Danko Laplace operator is already invariant. So this is the content of the last row. Okay. So how this can be used to modify or to construct certain objects of interest. So as I said, the content of ambient metric construction was explained by previous speakers. So just roughly speaking, this is the device which allows to treat some problems on conformal manifolds on associated pseudo-Riemannian space of 2 dimensions higher than this manifold M. And in particular, we will be interested in the flat case. So in this situation, our manifold M, either, okay, let M in the case of interest be n-dimensional sphere. So in this case, the sphere or conformal sphere is realized as a projectivization of certain quadric or of real vector space of signature p+1, q+1. Okay, so this quadric is cone of null vectors, and the projectivization is just our flat conformal manifold, in particular the sphere. Okay, so quickly or briefly, the operators we will look at will act on density. So once again, a density on a conformal manifold can be regarded as a homogeneous function on the hypersurface C in the ambient space. and the standard construction of those non-standard operators, so operators whose symbols are powers of Laplacian, are given as follows. So first we take a corresponding density represented by a homogeneous function on the null cone, and then we apply the ambient Laplacian or power of it, and then to certain extension of a corresponding density of the cone, and then we will restrict back to C, to the null cone, and for a suitable choice of the density, this procedure is independent of extension, and we will construct some manifestly conformally invariant operators. Okay, so what we will need, okay, what is the crucial point in this construction of non-standard operators, GJMS operators, is certain SL2 algebra. And this is sufficient to construct these operators. In particular, this construction I'm going to present is based on certain modification of this SL2 algebra. So there are three operators acting on smooth functions in the ambient space. The operator E is the square up to certain factor, square of the length of vector x, which is the one already appearing in the standard construction of GJMS operators. However, the operators f and h include, so the operator f is this Dank Laplace operator, and the operator h is Euler operator up to trace of the multiplicity function, which is this gamma k. Okay, so here is the explicit form of this Dank Laplace operator. So it contains certain differential parts, like this Laplace part, and there is gradient of the function to which this operator is applied. But in the end, the third term is just the reflection of non-local term. Okay. So having this SL2 algebra, one can apply analogous construction like in the standard case of standard conformal geometry, meaning we will start with certain densities on a manifold M, and once again I should emphasize that M should be thought of as sort of the sphere. So we shall start with densities, and then we understand or regard these densities as W homogeneous functions on the cone, on the null cone. And we can extend these densities to a given density to the ambient space. And after the action of the power of this Laplace-Dankel operator, restrict back to the null cone. So, okay, so I forgot to emphasize on the previous slide that at this point, I mean, the finite reflection group G is chosen. So this is the basic data which one chooses. Okay. So the following theorem is just the claim which is parallel to the standard reasoning when GJMS operators are constructed, in particular for each natural number and certain weight W, which is minus n half plus j minus the trace of the multiplicity function. When I use the same composition, so first having this density, then extending, then applied the power of Dankel Laplace operator, and then restrict back to the null cone. So for this special value of W, this construction is independent of extension, and consequently it uses G when, once again, G is this finite reflection group, G invariant differential difference operator on the n-dimensional sphere acting between corresponding induced representations from W and W minus 2J density. And this operator is over 2J, and this operator is, and for each J, this operator is non-trivial. Okay. So this is abstract reasoning, so this is existent theorem for such operators and non-triviality and non-triviality claim for these operators. Okay. Another matter is then explicit construction of these operators when one takes a representative matrix and computes in coordinates explicit form of them. So this will this is not a topic I will discuss here. And the last remark I should mention that as in the case of standard GJMS operators, so these operators should be related to abstractions to harmonic extension from the null cone to the ambient space, meaning to, in this case, to extend a given section or a given homogeneous function of the null cone as a solution of this Danko-Laplace operator. Okay, but I didn't investigate this line of thought. Okay, that's all I wanted to say. Thanks for your attention. Yeah, of course.
Is there some motivation or application, intended application for this?
Okay,
be something that might have to do with something.
Okay, so okay, one of these geometric motivation is that in ordinary Euclidean space, having a root system, one considers reflections along hyperplanes corresponding to the roots or orthogonal to the roots. On the sphere, the corresponding property is that the action of the finite reflection group is the finite reflection group related to reflection along certain hypersurfaces, explicitly along spheres, and wider motivation just these finite. I mean, one particular example of a finite reflection group are the Weyl groups of Lie algebras or Lie groups, and there is, I mean, a huge interest behind invariant theory or harmonic theory for finite reflection groups starting from these integrable systems like Kalogerov-Moser, Perelmov-Olshansky, I don't remember all of those names. And also purely mathematically, these notions, I mean, culminated in the mathematical notion behind harmonic analysis for finite reflection groups is called Schrödinger algebra. So okay, that's all reasonable I can say.
Could there be some conformally invariant integrable systems related to these differential differences?
Yeah, that's one of the aims. So that should be one of the aims where these operators could be useful. So to produce, to manufacture conformal invariant version of usual consideration. So usually these finite reflection groups are considered as a subgroup of Levy factor, let's say, from the point of view of conformal geometry. But now you can consider the question how the picture changes when these finite groups are considered as subgroups of conformal group.